Hello all. Suppose that an object is moving and it is acted upon by a net force. We suppose that it moves from a point A along this path to a point B, and we calculate the work done by force as the particle move along this path. We know that work done is equal to integration from initial position to the final position of F bar dot ds bar. F bar is the force acting and ds bar is the small displacement produced at any point of its path. Now we use Newton's second law of motion. According to Newton's second law of motion, F bar is equal to ma bar, and we can write acceleration as rate of change of velocity. Moreover, the displacement ds bar it can be written as the velocity time the small time interval dt in which the displacement takes place. We substitute for F bar and ds bar in this equation and obtain work equal to integration from A to B m dv bar by dt, and we must write dot because it is a dot product between vectors. ds bar is equal to v bar into dt. Now d by dt derivative of the dot product between velocity vectors. We can write this derivative using product rule as v bar dot dv bar by dt plus dv bar by dt dot v bar. These both the terms are equal. So we can write 2 times dv bar by dt dot v bar, and hence this gives us dv bar by dt equal to 1 half d by dt of the dot product. On the left hand side it is dv bar dot v bar. So having obtained dv bar dot v bar equal to this, we substitute this here in the integration and obtain for work is equal to integration from A to B m into half d by dt of v bar dot v bar and then dt. V bar dot v bar is simply the velocity square. We further write it as integration from A to B. We take half outside the integration, and the mass m can also be taken outside the integration because it is constant, and then write d by dt of v square time dt. In the next step, we write integration from A to B. Derivative of v square with respect to time is 2v dv by dt. These are the simple results known from calculus. dt get cancelled and we get work equal to half m integration from A to B to v dv. Now we have obtained the integration where the variable of integration is the velocity. We started with the definition of work, and now we have arrived at an integration where the variable of our integration is the velocity. So we have an integrand that is a function of velocity. Velocity for this integration is an independent variable. At the beginning, which is denoted by a point A, there is a certain value of velocity. We denote the velocity at position A by VA and the velocity at position B by VB, and replace the integration limit by velocity limit, and we get work equal to integration from VA to VB to V dV. And the integration, wait, something is missed. We have to write half m outside the integration, and then we have half m. The integration is v square and the integration limits are VA, VB. So we have W equal to half m VB square minus VA square. The velocity at point A can be taken as the initial velocity, and the velocity at point B can be taken as the final velocity, Vf. With this replacement, we get work equal to half m Vf final velocity square minus initial velocity square. And finally, we have work equal to half mvf square minus half mvi square. This equation has a special significance. We know that the energy is a capacity to do work. If the work is done on a particle, it must have been done at the expense of energy by some external agent. External agent loses the energy, and that energy is utilized in doing this work on a particle. So the external agent which does the work, it has lost the energy, and that energy has transferred to the particle upon which the work is done. So whenever work happens, there is a transfer of energy. The transfer of energy from doer to an object upon which the work is done. And here we see that the work done is equal to change in this quantity, half mvf square and half mvi square. This is a significant quantity. We can interpret this equation as change in the quantity defined as half mass time velocity square. We define a quantity, we denote it by k, as half mvf square. And now we can interpret the equation for work as the change in this quantity, final value of this quantity minus initial value of this quantity. Now the work is done on a particle. So a doer loses the energy and the same amount of energy is gained by a particle upon which the work is done. The amount of energy gained by a particle will be equal to the work that is done, because energy is simply the work done. And here we see that the change in this quantity is exactly equal to the work done. This quantity changes as a result of work being done on it. So we can identify this quantity as a form of energy which changes because of the work done on it. Because when the work is done on a particle, there is a transfer of energy from doer to a particle, from external agent to a particle. And if the change in this quantity is exactly equal to work, then according to the definition of work, which we take as equal to the work done, this quantity must represent some energy form which increases or decreases as a result of work done upon it. When the work is done on a particle, this quantity increases because the velocity, final velocity of the particle will be greater. and therefore this quantity will be greater at a final moment. So increase in this quantity is equal to work done. This means that the quantity must be a form of energy which increases as a result of work done, and the increase in this quantity is exactly equal to work done. This quantity is therefore of a special significance. It represents the energy in the form of motion. We call this the kinetic energy of a body. So we now identify the kinetic energy of an object. Kinetic energy as k equal to half mass time velocity square. And we have a result that the work done is equal to change in kinetic energy, final kinetic energy minus the initial kinetic energy. This result is known as work kinetic energy theorem. Work kinetic energy theorem. So we have found that the work done on a particle as it moves from the position A to position B is equal to the change in kinetic energy. Will the change in kinetic energy remain the same if the particle follows some other path? For example, if particle moves from the position A to position B along this path, then what about the change in its kinetic energy? Well, the change in kinetic energy may depend upon the path followed in going from the same in going from the same initial position to the same final position. It may depend upon the path followed, the change in kinetic energy. But if change in kinetic energy depends upon the path followed from initial position to the final position, then the analysis of problem will become somewhat difficult. We can consider an easier version of this problem in which the change in kinetic energy as it goes from initial position to the final position does not depend upon what path it takes. Whichever path the object follow from given initial position to the given final position, if the kinetic energy remains the same, then the problem, the analysis of the motion become easier. Now, if the kinetic energy does not have to depend upon the path followed, this in other words means that the work done by force will not depend upon the path followed. Whichever path the particle travel from a given initial position to the final position, if the work done by the force is always same, then the change in kinetic energy will also be always changed according to the work kinetic energy theorem. So we now consider the problem in which the work done on a particle does not depend upon path between the two positions. The forces which satisfy this condition, that the work done by them does not depend upon the path between the 2 points, but it only depends upon the 2 points themselves. Such forces are called conservative forces. Conservative forces. So, for conservative forces, again we suppose the two positions between which the particle move, position A, and it moves to the position B along the path number 1. Say this is the path 1. Several paths are possible between the two positions. I take another path connecting the two positions as, say, this is the path number 2. And these are any two paths connecting the two positions. And for any two path, if the work done along path 1, along any path 1 is equal to the work done along any other path, the path 2, then the forces are said to be conservative. Work done in going from A to B. The direction of motion is from A to B. Also, the work done in moving from B to A along say path 2, along path 2, work done in moving from, now we consider the work done along a given path in either of the direction. From the definition of work, which is the integration of a bar dot ds bar along a certain path from point 1 to point 2. If we move from point 2 to point 1 along the same path, then only the direction of the displacement reverses. So, in the present case, the direction of displacement will be opposite to the direction of displacement in the first case. So, we write a negative sign and we get work, say we denote it by W dash. Or we denote this work done as 1, 2 in going from position 1 to position 2, and the work done in the second case where we move in the reverse direction from position 2 to position 1, we denote it as 2, 1. So, we take negative sign outside and we get 2 to 1 a bar dot ds bar. Sorry, one mistake made here, a minor mistake. The work done in the reverse movement from the second position to the first position, we denote the displacement by say a ds2 bar, and here in this case we denote the displacement as ds1 bar. Now, in going from 2 to 1, the displacement ds2 bar will be opposite of the displacement ds1 bar, which is when we go from position 1 to position 2. It must be negative. So, we can replace ds2 bar by negative ds1 bar in this equation. Now at this point we have to look closely at these two equations. The displacement ds1 and ds2, they are opposite of each other. What we are doing is taking the integration along the same path by dividing the path into very small displacement segments. So, I show those displacement segments leading from position 1 to position 2. These are the displacement segments from position 1 to position 2. In the work done in going from position 1 to position 2, our displacement ds1, the displacement ds1 can be shown at any particular point of the path, say here, this is the displacement ds1 bar. While in moving reverse from position 2 to position 1, the displacement ds2, is opposite of displacement ds1. It is opposite of displacement ds1. This is ds2 bar. So, ds2 bar is opposite of the displacement ds1. So, here we can see that work done in going from position 1 to position 2, which we have denoted as integration from 1 to 2 into a bar dot ds bar, the force does not reverse the direction. Force remains same. It is a function of position. Force at every point of this path is same as before. It doesn't depend upon which way we are going, from position 1 to 2 or from 2 to 1. So, force remains same. So, we have no change there. Now, when we go in the reverse direction, what we have done, we simply have the negative values of the displacement. Simply the negative values of displacement. So, the work done in going from position 2 to 1, it is not necessary that we start from 2 and go to 1. We can see that for every segment, the displacement for work W12 is ds1 bar and the displacement for the work W21 is negative of ds1 bar. So, work done in going from 2 to 1 can be written as integration from 1 to 2 with the ds bar replaced by negative of ds1 bar, and this is equal to negative of integration from 1 to 2 a bar dot ds1 bar, and this is nothing but the work done in going from 1 to 2. So we find that work W12 is equal to negative of the work, sorry, on the left hand side we have W21. Work W21 is equal to negative of the work from 1 to 2. And this means that the work done in going from point 1 to 2 and the work done in our reverse journey, which is W21, the sum of the work is equal to 0. Also, in conservative forces, the work done depends only upon the two positions, initial and final position. It doesn't depend upon what path is followed. Now, we consider two paths again between the two positions, position 1 and position 2. One path going from position 1 to position 2 like this, and we come back to position 1 but via some other path, so that we have a round trip journey between the position 1 and position 2. We go from 1 to 2 and then come back from 2 to 1. So this is a round trip journey. What will be the total work done in this round trip journey? The total work done in the round trip between the two positions, I write total work in round trip the total work done may be written as work done in going from point 1 to point 2, that is W12, and going from point 2 to point 1, but now along a different path, W21. This is the work done W12, and work done along this path is W21. Let's this work be called W-21 for the reason which you will soon understand after we derive an important result. W-21. This equation states that the work done in going from point 2 to point 1 and the work done in going in the reverse direction from point 1 to point 2, they are negative of each other. But these two works are considered along the same path, but only in the reverse direction. Now, W-21 is the work done along the second path, a pink color path from 2 to 1. Now, if we consider the work along the same pink path from point 1 to point 2, we denote that work done along the second path. This is the second path, and this is the first path. Work done in going from 1 to 2 along this second path. This work done from 1 to 2 is negative of W-21 because along the same path, work done in the reverse directions are negative of each other. So, work done in going from W1 to W2, work done in going from position 1 to position 2 along this pink path will be the negative of this W-21. We denote this work by W-12. W-12. So, we have total work done. We are talking about conservative forces. For conservative forces, the work done in going from point 1 to point 2 is same irrespective of which path we follow. So, work done in going from point 1 to point 2, which we have denoted as W-12. This is equal to the negative of the work done along the same path in moving in the reverse direction. So, we can write W-21 equal negative of W-12. Now W dash 1 2 represent the work done in going from point 1 to point 2 along second path, but it must be equal to the work done along the first path in going from the same point 1 to same point 2, because it is a conservative forces. So for a conservative forces, the work done W dash 1 2 is equal to W 1 2. Only the paths are different, but the 2 points between which the moment the particle is moving is same. So W dash 1 2 is equal to W 1 2. This means we have W dash 2 1 equal to negative. We substitute for W dash 1 2. For W dash 1 2, we substitute W 1 2 here, and we get W dash 2 1 equal to negative of W 1 2. And now for W dash 2 1, we substitute negative of W 1 2 here in this equation, and it will give us W equal to W 1 2 plus W negative W 1 2, and we have a result that the work is equal to 0. But what was this work? This work was the total work done in a round trip between the point 1 and point 2, going from 1 to 2 along one path and back from 2 to 1 along some other path. So our path was a closed path. So we can say that the work done along a closed path when the forces are conservative is 0. So when the work done is 0 along a closed path, we can take this fact as an alternative definition of conservative forces. So we can say that the conservative forces are those in which the work done along closed path is 0. So I write the statement, the work, sorry, we write it like this: the forces are conservative when the work done along the closed path is 0. By closed path means from whichever point you begin, you will come back to the same point after tracing along that path. So this is a kind of closed path.